So, good evening and welcome back to this problem solving session for the NPTEL course Geology and Soil Mechanics. So, the last class we solved a few numerical problems regarding consolidation. So, how to estimate the primary consolidation settlement of a soil due to the application of some uh, pressure or we can say load at the surface of the soil. So we mostly uh, discussed about the magnitude, that how to determine the consideration settlement. Now in this week we'll be discussing about the time rate of settlement. So to reach a certain percentage of the estimated or expected settlement, how much time the soil will take. So this is the main topic for today's discussion. Okay, so I have selected a few problems. Through solving these problems we'll be trying to learn this topic to some extent. Okay, so we'll not uh, delay further. So with this brief introduction we'll start today's session with this problem. So this problem was asked in GATE examination 2022. So in this problem, a raft foundation of size 30 meter by 25 meter is proposed to be constructed at a depth of 8 meter in a sand layer. A 25-meter thick saturated clay layer exists 2 meter below the base of the raft foundation. Below the clay layer, a dense sand layer exists at the side. Now, a 25 mm thick undisturbed sample was collected from the mid-depth of the clay layer and tested in a laboratory odometer under double drainage condition. It was found that the soil sample had undergone 50% consolidation settlement in 10 minutes. Therefore, the time required for 25% consolidation settlement of the raft foundation will be. Now, it's very clear from the problem statement that two conditions are talked about in this problem. So the first one is the lab condition, or rather we can say laboratory condition. And secondly, the field condition. Now what we can see from this problem statement, that a sample, an undisturbed sample of 25 mm thickness was collected from the field and it was tested. Now after testing, it was found that the soil sample required 10 minutes to reach 50% concentration settlement. Now what would be the time requirement or the required time for 25% concentration settlement in the field condition? So anyhow, we have to extrapolate the laboratory data to the field condition. So this is the main objective of this problem. So we'll see how we can extrapolate the data of laboratory to the field condition. So before that, we'll try to visualize the problem statement. So for that, we'll first draw the problem sketch and then we'll proceed further. So as mentioned in the problem, that there is a raft foundation of size 30 meter by 25 meter. So suppose this is the raft, this is the raft foundation, of size 30 meter by 5 meter. So this is the raft foundation. Okay, so though as of now we we are not familiar with the foundation, the terminology foundation, because it comes under the course foundation engineering. So that we'll learn in the in some advanced level course. Okay, so this course, soil mechanics and geology, and soil mechanics, so this is the fundamental course. So once the topics or the knowledge, we have an in-depth knowledge of this course, about this course, then it will be much easier for us to grasp the concept of the subsequent courses like foundation engineering. Okay, so right now we'll confine ourselves uh, to the topic of consolidation. Okay, so we'll not go to the details of foundation, what is foundation, or more specifically what is ref foundation. So it's a special kind of foundation that you can learn from the foundation engineering course. Okay, now this foundation is proposed to be constructed at a depth of 8 meter in a sand hill. So this is the, if this is the ground surface, then the depth of foundation, this is known as depth of foundation. So this is your 8 meter, and the soil is sand. Okay, now in the next statement, a 25 meter thick saturated clay layer exists 2 meter below the base of the raft foundation. So this is the base. So this is the base. Now below this base, 2 meter below the base, so this is your base level, and 2 meter below, so this is your meter, there is a 25 meter thick, 25 meter thick saturated clay. Okay, so this is your 25 meter. So this sketch is not as per the actual scale. Okay, so please remember that. So this is the saturated clay. And this is your sand. Now below the clay layer, a dense sand layer exists at the side. So below this saturated clay, there is one more layer, and that is dense sand. So this is your dense sand. Okay. Now with this soil stratigraphy, or with this soil layering, a 25 thick undisturbed sample was collected from the mid depth of the clay layer. So if this is the mid depth, suppose from here a sample is collected, sorry, so a sample is collected, and the thickness of this sample is 25 mm. So this is tested in the laboratory. Now it was found that the soil sample had undergone 50% consolidation, 50% consolidation in 10 minutes. Okay, now the question is, then how much time in how much time the RAF foundation will achieve 25% consideration settlement. So the question, so if your U is equals to 25%, then what is the required time, and that we need to be estimated in days. Okay, so this is the problem statement. Now we'll start from the laboratory condition. So laboratory condition, so since your degree of consolidation is 50%, so we can easily determine, okay, so before let me put the term laboratory. So your U percentage is 50%. So you can easily determine the TV value. What is TV? So it is the time factor. Okay, so it is the time factor now. This time factor we can determine from this equation, pi by 4 Q divided by 100 square, when your U percentage is less than 60%. Okay, now if it is more than 60%, then you have to calculate this time factor from this equation, 1.781 minus 0.933 log of 100 minus U, if it is greater than 60%. Now since for the present problem it's less than 60%, so we'll use the first equation. Therefore our TV would be pi by 4 multiplied by 50 by 100 square. So it's 0.197. Okay, now again we know that TV equals to CV T divided by H dr square. Now what are these terms? So here CV is your coefficient of consolidation, T is your time, and H dr, this is the drainage path. Drainage path. Okay. Now for the laboratory condition, we know this value T, time, and the drainage path name. How? So the time is 10 minutes for 50% consolidation as mentioned in the problem statement, and the drainage path length or drainage path distance is your 25 by 2, that is 12.5 mm. Why? Because it's explicitly mentioned in the problem that the soil sample was tested in the laboratory odometer under double drainage condition. So therefore, if it is double drainage, so drainage path will be half of its thickness. So for double drainage, your HDR equals to H, that is the thickness of the sample, and for single drainage, HDR, oh sorry, H upon 2, and for single drainage, it is simply H. When the drainage is basically happening only on the single side of the sample. Okay, so if there are two-way drainage, then the drainage path distance would be simply the thickness of by 2, half of its thickness, and for single drainage, the drainage path distance or drainage path length will be simply the thickness. Okay, so this is very much essential to calculate the time rate of consolidation. So therefore we know HDL, we know T, and we know TV. So from this equation, we can calculate the value of coefficient of consolidation. So CV would be TV HD square divided by T. Okay, so this is the formula for the coefficient of consolidation. Now if we so now if we substitute the values, of H, deer, and T in this equation, then CV will get, the CV value would be your TB, which is 0.197, then HDR square, that is 12.5 square divided by 10. So that means .08 millimeter square per millimeter. Okay, so we have got the coefficient of consolidation. Now please be very careful about this CV, because this CV is nothing but the CV of the soil at the field. So we have basically collected a sample from the mid depth of the clay layer, and that sample was tested in the laboratory. So whatever CV we have now obtained from the laboratory experiment, that is nothing but the CV of the clay layer, saturated clay layer, which is at the field condition. So this CV will remain same. So as long as we are dealing with the same soil, this CV will not change. Now we'll be coming to the field condition. Okay. Because our target is to determine the time of consolidation settlement of the RAF foundation. So therefore, now we'll have to calculate the TB for the new degree of consolidation, because we would like to calculate the required time for 25% consolidation. So therefore TB will change depending on the degree of consolidation. So here your U percentage is 25. So therefore your TB will be pi by 4, 25 by 100 square. Again, your U percentage is less than 60, therefore we'll use the first equation only. Okay, so it's 0.049, and your CV value already we have calculated, and that is 3.08 millimeter square per milli. And what is the value of HDR? So HDR for the field condition, it will be again a double drainage condition. How? Because on the top of the clay layer, saturated clay layer, it's sand, and again in the bottom of the clay layer, it's dense sand. So that means the saturated clay layer in the field is sandwiched between two clay layers. So drainage can occur from the top as well as from the bottom. Okay. So therefore, your drainage path distance, it will be half of the thickness. So this is your HDR. Okay. So similarly, this is also your HDR. So therefore, your HDR value for the field condition will be, what is the thickness of the saturated clay layer? It's 25. Therefore, 25 by 2, that means 12.5 meter. Now, we'll use the same equation, that is TB equals to CVT by HDR square. So therefore, your T will be TB HDR square by CV, and TB value is 0.049. HDR square, we have to be very careful about the unit system. So since we are using CV in millimeter square per minute, so it has to be converted to millimeter. So 12.5 into 1000 millimeter square divided by 3.0. So if we calculate 0.049 multiplied by 12,500 square divided by 3.08. So it's 2485 795.46 minutes. However, we have to report the time in days. So therefore, this value we have to divide it by 60 So it will be in hour, then again by 24, then it will be in days. So divided by 24 into 60. So approximately 1727 days. And this is the answer. Okay. So this much time will be required for 25% consolidation settlement of the RAF foundation to occur. Okay. So through this problem, we have seen when we know the time or some percentage of consolidation for a laboratory sample, we can easily extrapolate that data to the time rate of settlement of the field from where the sample was collected. So please keep in mind that for this kind of extrapolation, the sample and the field soil should be same. Means the soil should be collected from the field, same field. Okay. Otherwise, we cannot use the same data, same CV for another field condition or any field condition. So that is not be the correct approach. So from the laboratory data, we'll first calculate the coefficient of consolidation. Now, once this coefficient of consolidation is known to you, you can calculate the time requirement for any percentage of consolidation, because depending on the percentage of consolidation, you can calculate the time factor, and from this time factor, you can calculate the time requirement. Okay. So this is all for this problem. Now we'll take problem 2. So this is related to a 3-meter thick clay layer beneath a building, which is overlain by a permeable stratum and is underlain by an impervious rock. The coefficient of consolidation of the clay was found to be 0.025 centimeter square per minute. The final expected supplement for the layer is 8 centimeter. Now we have to answer 3 questions. The first one is, how much time will it take for 80% of the total settlement to take place? This is question 1. Second question is, determine the time required for a settlement of 2.5 centimeter to occur. And finally, compute the settlement that would occur in 1 year. So this is a very similar kind of problem to problem 1, except for the calculation of coefficient of consolidation. So earlier in problem 1, we had to calculate the coefficient of consolidation based on the odometer data. However, in this problem, the coefficient of consolidation value is directly provided to us. So there is no requirement of such calculation. Rather, we can directly proceed for the calculation of required time for a certain percentage of degree of consolidation. Okay. So we'll first draw the field condition or the soil layering. So there is a 3-meter thick so this is your 3-meter thick clay layer. Now on top of this clay layer, there is a permeable stratum, and bottom there is an impervious rock. Okay. Now, what is the physical significance of this statement? The physical significance of this statement that the drainage will occur, or the drainage will take place in this problem only from the top of the clay layer. So therefore, your drainage path length will be the total thickness of the clay. Okay. So this is the significance, physical significance of this statement. Now, as per the problem, what is the value of coefficient of consolidation? The CV value is 0.025 centimeter square per minute. And what is the final expected settlement of the layer? So S8, the final expected settlement of the layer is 8 centimeter. Now, for the first question, we'll try to answer how much time will it take for 80% of the total settlement to take place. So therefore, question number A, so U percentage is your 80. So the corresponding time factor we can easily calculate from this equation, 1.781 minus 0.933 minus 80. So it will be 0.567. Okay. Now, your TV is CVT by HD square. Okay. So rather, let me first establish a relationship between TV and T. Now, we know the value of CV. The CV value is your 0.025 multiplied by T and HD square, that means 300 square. So therefore, your T value would be 3.6 into 10 to the power 6 dB. Okay, so this is the relationship between the time and the time factor. So if we know the TV for a given percentage of consolidation, therefore we can easily calculate the required time. So for example, we know the TV value for 80% consolidation and it's 0.567. So therefore, the required time, suppose this is your equation 1, the required time will be 3.6 into 10 to the power 6 TV is your 0.567. And please be careful that whatever time we'll get from this equation, that will be in minutes. Okay, from equation 1. So this will be in minutes. Okay, so we'll convert this minutes to years. So therefore, First, it will be 204,1200. That should be divided by 16, then 24, then 365. Okay. So it's approximately 3.89, 3.88. So this is the answer to question 2A. Okay. Now we'll take the next question of this problem, that is, determine the time required for a supplement of 2.5 centimeter to occur. So in this problem, in this question, the degree of or percentage consolidation is not directly mentioned. Rather, the value of supplement is mentioned. So therefore, we have to first calculate the percentage of consolidation, and it will be the supplement at a specific time divided by the expected final settlement multiplied by 100. Now in this question, what is the settlement? 2.5. So 2.5. And what is the final settlement? The final settlement value is 8 centimeter. So 2.5 by 8 multiplied by 100, that will give you the degree of consolidation. And it's 31.25%. Now, once we know the degree of consolidation, we can calculate the TV value from this equation. Okay. Again, it's less than 60. So we'll use the first equation, and the TV value would be 0.077. Now, the required time, that would be 3.6 into 10 to the power 6 times TV. So 3.6 into 10 to the power 6 times 0.077. Again, this is from equation 1. Okay, this is in minutes. So 3.6 into 10 to the power 6 multiplied by 0.077, it's 277,200 minutes divided by, so 60 multiplied by 24. That means approximately 193 days. Okay. So this is the answer for question 2B. So as I mentioned earlier, so once we know the relationship between the time and time factor, we can easily calculate the required time for any percentage of consolidation. Now, to establish the relationship between time and time factor, we need to know the drainage path length and the coefficient of consolidation of the soil with which we are dealing. Okay. So in this way, we can answer any question. Now, in the final question of this problem, we have to compute the supplement that would occur in 1 year. So it's a reverse problem. So in the earlier two problems, or in the earlier two questions, we have seen a certain percentage of consolidation was given. Just we have to reply how much time the soil or clay layer will take to achieve that much percentage of consolidation. Now, in the final question, it's a reverse scenario. Here, the time frame is given. We have to calculate the settlement. How much settlement will occur of the soil of the clay layer? Okay, in within this time frame or within this duration, or rather, we can say at the end of this duration. So therefore, we have to approach in a reverse way. So first, we'll calculate the TV. So see, since your T is given as 1 year, that means 365 multiplied by 24 multiplied by 60. So this much minutes, okay? So 365 multiplied by 24 multiplied by 60. So 5.25 into 10 to the power 5. So 5.26 into 10 to the power 5. Now again we'll use the equation 1. So T is equals to 3.6 into 10 to the power 6 TV. So this is your equation 1. So therefore your TV value would be 5.256 into 10 to the power 5 divided by 3.6 into 10 to the power 6. So the value would be 0.146. Now if your TV value is 0.146, so what we have to do? We have to back calculate the percentage of consolidation or the degree of consolidation for which the TV value should be 0.146. So how we can calculate? Because we have two equations for the calculation of TV. So one is for degree of consolidation get less than 60%, another one is for greater than 60%. Now we know from the earlier problem that your TV value is 0.197 for a degree of consolidation of 50%. So obviously for a TV value of 0.146, the degree of consolidation should be less than 50%. It's on the lower side. So we'll use this equation. So pi by 4 u100 square. So therefore your u will be 4 TV by 100 multiplied by 100 root square root. Okay, so therefore 4 into 0.146 multiplied by 100 divided by 5. So it will be 'sorry, I think I did a mistake here. So please correct. So first you have to calculate the square root of this entity, then you have to multiply 8 with 100. So it's approximately 43%. Okay. So we have calculated the degree of consolidation for within or after 1 year. So in 1 year, 43% consolidation we can expect or we can achieve. So if the degree of consolidation is 43%, then what would be the settlement value? So settlement value, again, you know that ST by SA, so this is your 0.43. Therefore, ST will be 0.43 multiplied by SF or 0.43 multiplied by 8. 0.43 multiplied by 8, that means 3.44 centimeter. Okay, so this would be the expected settlement after 1 year. 3.44 settlement, 3.44 centimeter settlement. So your ST is 3.44 centimeter. So this is the answer. So therefore, for to answer this type of questions, we should have an in-depth knowledge about the definition of degree of consolidation, time factor, then your what I can say, the relationship between time factor and the coefficient of consolidation. Okay, so if we know these things uh, in a very in-depth manner, then we can answer any questions pertaining to time rate of consolidation. Okay, so with this, I think this problem is done. Now we'll take the next problem, that is problem 3. So in problem 3, a homogeneous clay layer of 12 meter thick is expected to have an ultimate settlement of 332 millimeter. Now, after a time span of 3 years, the average settlement was measured to be 152 millimeter. Now, how much longer will it take for the average settlement to attain 237 mm? So, in this problem, what we can see, the ultimate settlement, that is SF, is given, which is nothing but 332 mm. Then for a time span T1, which is equal to 3 years, the average settlement, measured average settlement, is given as 152. Now we have to determine a time T2 for an average settlement of 237. So this is the question. We know the average, we know the ultimate settlement, which is 332 millimeter, and we know the time frame, the duration or the required time for an average settlement of 152 millimeter, which is 3 years. Now we have to calculate the time for another settlement value, that is 237 millimeter. Now how we can solve this problem, that we'll see in the subsequent course. Okay, so our first job to answer this question, our first job would be to determine the degree of consolidation. Now to determine the degree of consolidation, so it will be simply, suppose if we denote for the first case as U1, so it will be S1 by SF multiplied by 100. Okay. Now your S1 is 152 and your SF is 332. So obviously the degree of consolidation would be 45.78 percentage. 45.78 percentage. Now coming to the second case where your S2 value is given as 237 millimeter. So the degree of consolidation would be 237 divided by 332 multiplied by 100, that is 71.39. 71.39 percentage. Okay. So now we know the degree of consolidation for both the cases. So once we know the degree of consolidation, we can calculate the time factor corresponding to these cases. So TV1 and your TV2. Now which equation to use? So that will depend on the degree of consolidation. So for the first case, since the degree of consolidation is less than 60%, so we'll use this equation, pi by 4 multiplied by u1 by 100 square. And for the second time factor, since the degree of consolidation is greater than 60%, so we'll use this equation, 1.781 minus 0.933 log of 100 minus 2. Now we'll substitute the values. So for the first case, your U1 percentage is 45.78, and for the second case, your U2 percentage is 71.39. Okay. So if we calculate, then these two values would be so for the first one, it will be 0.1646. So this is 0.1646, and for the second case, your TV value would be 0.4221. Okay. Now we'll again utilize this relationship that TV equals to CVT H dr square. Now please observe very carefully that here we are not changing the soil. We are dealing with the same soil layer, that is a homogeneous clay layer of 12 meter thickness, and therefore this CV value and this drainage path length HDR will be constant. So for this specific layer, your CV and HDR, this will not change, this will be constant. Okay, this will remain same. Now in this equation, if the CV and H dr square value remains same, that means your TV is basically proportional to T. Now your TV is proportional to T, then you can write this T1 upon T2, or the other we can say TB1 by TB2 equals to T1 by T2. So therefore your T2 will be T1 multiplied by TB1 divided by TB2. Okay, so this would be the this would be the calculation for time to t2 time. Okay, now what is the value of tb1 and tb2? So tb1 is your just let me check it once. I might do a mistake here. Yeah, so this would be the reciprocal. So tv2 by tb1. Now what is the value of t1? So the t1 value is your 3 years. Okay, what is the value of tb2? tb2 value is your 0.4221, and the value of tb1 is 0.1646. So it's approximately 7.6 million. Okay, so this is the answer. Okay, so in this problem we are given the total or the final supplement, ultimate supplement. We are given the time span for a specific supplement, measured supplement. Now we need to calculate the time frame or the duration for another supplement. So for example, the final ultimate supplement was given as 332 millimeter. Now in 3 years, the average supplement which is measured is found out to be 152 millimeter. Now we have to calculate the time which is required for an average supplement to attain a value of 237 millimeter. Now what we have done to solve this problem, we have first calculated the degree of consolidation for both the cases. We have then calculated the corresponding time factor. Then from the relationship between TV, CV, T and H year square, we 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 have found that the time factor is proportional to time, since the CV and H year is constant for the given layer. Okay, the coefficient of consolidation is remains same for the soil, and again the drainage path distance also remains same. So therefore we can say this tb1 by tb2 equals to t1 by t2, and from there we have calculated the t2 value as 7.69 years. Okay, which is the time required for an average supplement to attain a value of 237 liter. So is it okay? Is it okay for you? Okay, so I am not getting any response from your end, so I am assuming that it's fine. Now we'll proceed to the next problem, and this is a problem. It will cover all the topics which we have learned from the previous week as well as from this week. So this will cover first the calculation of primary consolidation supplement from the very beginning. Then it will also help us to demonstrate how to calculate the time supplement plot. Okay, so therefore from the as a practicing engineer, or from the practicality point of view, this problem is very essential. Okay, so please be very careful about each and every step which are involved or which is involved to solve or address this problem. Okay, so first let me uh, read the problem. So a foundation for an oil tank is proposed for a site with a soil profile as shown in figure. So this is the soil profile. Now from this soil profile, as we can see, So there is three layers of soil. The first or topmost layer is sand, and within this sand layer, the groundwater table was located. So it's located at a depth of 2 meters from the top surface. Then the sand is underlain by a fine grained soil, which is basically a mixture of clay and silt, and then it's underlain by a fractured rock. So this is the soil layering upon which a foundation for an oil tank is proposed. Now a specimen of the fine grained soil 75 mm in diameter and 20 mm thick was tested in an odometer in a laboratory. The initial water content was 62%. Specific gravity of soil solids is 2.7. The vertical stresses were applied incrementally, each increment remaining on the specimen until the pore water pressure change was negligible. So this is talked about the uh, standard procedure of laboratory consolidation test. Okay, so we apply the load in an incremental manner, and we keep the loading increment on the specimen until the pore water pressure change was negligible. Now, the cumulative settlement values at the end of each loading step are as follows. So this table talks about the cumulative settlement. So please be very careful about this term. Cumulative, not individual settlement. The cumulative settlement at the end of each loading step. So suppose first loading or vertical stress of x1 or p1 or sigma 1. Suppose sigma 1 is applied. So for that we have observed a settlement value of s1. Now for the next increment, the loading magnitude of the stress magnitude is increased to sigma 2. Now for that we have observed not an individual settlement, accumulative settlement of H2. Okay, so in this fashion the data are recorded. In addition to this observation, the time settlement data for loading step from 60 to 120 kPa are also basically measured. Okay, and it's given in this table, the second table. Now the tank when full will impose vertical stresses of 90 kPa and 75 kPa at the top and bottom of the fine grained soil layer respectively. You may assume that the vertical stress is linearly distributed in this layer. Now, it's the additional stress which is mentioned in these two sentences. So when, as mentioned earlier, that this site is basically chosen for the construction of a foundation for an oil tank. Now, when this tank will be in the full condition, so it will impose vertical stresses. Obviously, it will impose vertical stresses, and these stresses will not be uniform throughout the soil thickness or the thickness of the layer. Now, at the top, it will basically impose vertical stress of 90 kPa, and at the bottom, it will impose a vertical stress of 75 kPa. And for the calculation purpose, so for the ease of simplification, it is mentioned that you can assume this distribution in a linear fashion. So as if the stress is basically distributed linearly from top to bottom of this fine grained soil layer. Is it fine? I hope so. Now what we have to do? We have to first determine the primary consolidation settlement of the fine grained soil layer when the tank is full. This is question number 1. And in the next question, we have to calculate and plot the settlement time curve for the field condition. Please be very careful for the field condition where the time settlement data for the laboratory condition are given to this problem. Okay, so now we'll proceed to solve this problem. So a few things that we have to take care before addressing or attempting this problem are that we have to first identify what kind of soil it is. Is it normally consolidated or over consolidated? Sorry. Okay. So the first question which will come in our mind, whether the soil is normally consolidated, the fine grained soil, or sorry, I don't know, I am facing a problem here. Please give me a few minutes to fix it up. Okay. Okay, sorry for the interruption. So the first question which will come to our mind, that whether the soil sample is normally consolidated, so it should come. Okay, so otherwise we'll be in a wrong way. That whether the soil which we are dealing with, so it's a normally consolidated type or over consolidated. And I hope that uh, by this time you must know what is the definition of this normally consolidated and over consolidated, because the calculation of primary consolidation supplement will be very much dependent on the type of soil. Okay, so that we will see. Now how we can identify, or how we can uh, come to a conclusion about the soil type, specifically normally consolidated or over consolidated. So we can come to that statement either by calculating or knowing the over consolidation ratio, or drawing the E versus log P plot, that is void ratio versus pressure plot in a semi logarithmic plot. Okay, so that for that we need to know the laboratory consolidation data, that we will see. Now once this is known to us, means the classification of the soil, classification in the sense normally or over consolidated, not that USCS or IS classification. Okay, so it is only for the calculation of primary consolidation, so please don't be confused. Now once it's known, so we know that your SC, for example, if we talk about the primary consolidation supplement of a normally consolidated soil, so it will be your CC divided by E0, then multiplied by H log of sigma 0 prime plus delta sigma prime divided by sigma 0 prime. So this is for normally consolidated. Okay. Now, what are the terms involved in this equation? So as we can see, Cc, E0, H, sigma 0 prime, delta sigma prime, and all these terms were defined in details in the previous session. Okay, so just for a brief introduction, this your Cc is nothing but the compression index, E0 is nothing but the initial void ratio, H is the thickness of the soil or the clay layer or the fine grained soil. Sigma 0 prime denotes the initial overburden pressure, effective overburden pressure at the mid depth of the clay or fine grained soil, and delta sigma, this is the increase in average stress at the mid depth of the layer. So these are the physical significances of these terms which are involved in this equation. So please be very careful. This equation or this expression of consolidation supplement will be valid only for normally consolidated. If this is not the case, means if the soil is over consolidated, then there will be some modification to this equation. Okay, so we'll not go at this moment, we'll not go into that details, because so far or as of now we don't know what kind of soil it is. So it will be better if we first identify the soil type, normally or over consolidated, then we'll discuss about the same. Okay. Okay, so what is Cc? Cc, this is the gradient of the linear part in the E versus log P plot. So therefore, our first job would be to establish the E log sigma prime. So this would be our first job, at least for this problem, and it will help for both to identify whether it is normally or over consolidated, and again to determine, it will help to determine the value of compression index. Okay, compression index or swelling index. That swelling index will be relevant for the case of over consolidated soil. So now to draw this E log sigma prime plot, we'll have to use this data, vertical stress versus settlement. So the first table, the data given the first table. So in the first row, vertical stress, and in the second row, the corresponding settlement value are given in this table. So therefore, to plot the void ratio corresponding to each load increment, we have to go through a few steps that we'll see now. Okay, so we'll first make a table, or we'll basically do this computation in a tabular fashion. So in this table, the first column would be sigma prime. Okay, so in kPa, this is nothing but the vertical stress. Now in the second column, it's a settlement. So please keep in mind, this is the accumulated supplement, not the individual settlement by the load increment. Okay, so this is the accumulated settlement, and if we denote this settlement by delta H, so it will be delta H for the second column of this table. Okay, so this is the accumulated settlement. Now, due to the application of this pressure, this vertical stress, what will happen? There will be a change in the void ratio, or more specifically, we can say there will be a deduction in the void ratio. So delta E, so that will calculate from the accumulated settlement at the end of each loading step. Now, once we know the change in the void ratio or the reduction in the void ratio, we can calculate the void ratio at the end of this step. Okay, so these are the few steps which we have to basically perform before having the data, the void ratio data corresponding to each vertical stress increment or uh, vertical stress increment. So we'll first write down all the stresses. So first 15 kPa, then 30 kPa, then 60, then 120, 240 and 480. So the stresses are applied from 15 kPa to a final value of 480 kPa. Okay, in an incremental manner. So first 15, then 30, 60, 120, 240 and 480. Okay. Now, what are the accumulated settlement observed for this kind of loading increment? So first 0.10, then 0.11, then 0.21, then 1.13, then 2.17, then 3.15. So as you can see, more the load is or more the vertical stress is applied to the soil sample, more the accumulated settlement is observed. So that means the sample is basically compressed. Now this reduction in thickness or this settlement can be related to the void ratio by change of void ratio method. Okay, so we had utilized this equation several times in the previous week. So your delta E divided by 1 plus E0 equals to delta H by H0. So this is the change of void ratio method. So by this method, we are relating the void ratio, the change in void ratio to the change in thickness. Okay, so these are the initial values. E0 is the initial void ratio and H0 is the initial thickness. Now what is the initial void ratio? What is the value for initial void ratio? So initial void ratio, it's not directly given to this problem. Rather, the initial water content and the specific gravity of soil solids are given to this problem. So from these two data, we can calculate. So we know that Wg equals to Ac. Now this value should be 1 for a fully saturated soil sample. So your E0 value would be W times GS. Now your W is 62% and GS value is 2.7. So 0.62 multiplied by 2.7, so 1.67, sorry. So this is the initial void ratio. And what is the value of H0? The value of H0 is nothing but 20 mm. This is the sample thickness before the consolidation. Okay. Okay. Now we can establish a relationship between delta E and delta H. So in this fashion, that 1 plus E0 divided by H0 multiplied by delta H. Okay, so through this problem, we are also learning how to utilize the data of a laboratory consolidation test to predict the settlement in the field. Okay, so this is an actual example of that kind of application. So 1 plus 1.67 divided by 20 delta H. So 2.67 divided by 20, that means 0.1335 delta H. Okay, so this is the final relationship between delta E and delta H. Now we know delta H for all this stress increment, so we can easily calculate the delta E value. So we'll calculate the delta E value one by one. So first of all, it will be 0.01335, then 0.01469, then 0.02804, then 0.15086, zero point 28970, and finally 0.42053. So these are the changes in void ratio corresponding to each vertical stress increment, starting from 15 kPa to a value of 480 kPa. Okay. Now, if these are the changes, then we can calculate the void ratio at the end of each load increment. How? So we can calculate the E value, the present E value, from this equation. E0 minus delta E. So as you are basically increasing the stress, your void ratio will be decreasing by this amount, delta E value. And all these changes, please be careful that all these changes are measured with respect to the initial value. Okay, so before consolidation, therefore we are basically deducting this delta E from the original void ratio value. So for the first load increment, the E value would be at the end of this 15 kPa stress increment, the E value would be 1.67 minus 0.01335, that is 1.66. Okay, so after rounding up, then 1.67 minus 0.041469, so it's again we can say 1.66, then 1.67 minus 0.02804, so 1.64. Okay, so one request to all of you that I may do mistake for the calculation part, so please cross check these values twice. Okay, then 1.67 minus 0.15086, that is 1.52, then 0.28970, that is 1.38, and finally 1.25. Okay, so these are the void ratios at the end of each stress increment. Now we can go for the plotting part. So we'll plot these two data, so this sigma 1, sigma prime, and the void ratio. So void ratio will be in the y-axis, and sigma prime or sigma z prime, it will be along the x-axis. And in addition to that, so please keep in mind that void ratio will be in the simple arithmetic scale, whereas the sigma prime value will be plotted in the logarithmic scale. So therefore it's a semi logarithmic plot. Okay, so these are the data point which we have calculated now. So this is 1.66 for a stress increment of 15 kPa, then this is again 1.66 for 30, this is for 60, this is for 120, this is for 240, and this is for 480 kPa. Okay, Now, after plotting this data point, what we have to do? We have to add all these data points to a smooth line. Okay. So this black dash, this black solid line, this is basically obtained by connecting all these data points. Now, you can visualize two trends. So first of all, these three data points, the up to this third data point, the slope of the line is very negligible, so very mild, then followed by a sudden steep gradient. Okay. Now this second line, the uh, gradient of the second line, second linear segment, so that is known as your CC, which is nothing but your compression index. Okay. So this will give you the gradient of the second linear segment will give you the compression index. So this will give you the compression index. Now how we can calculate the compression index? So it will be delta E by log of sigma 0 delta sigma by, or rather we can say sigma 2 prime by sigma 1 prime. So suppose this is your sigma 2 prime and this is your sigma 1 prime and this is your U1 and this is your E2. So therefore this value would be U1 minus E2 divided by log of sigma 2 prime by sigma 1 prime. Now what is the value of E1 corresponding to a value of sigma 1 prime? So sigma 1 prime means this value 120 kPa and sigma 2 prime is here 480. So E1 would be 1.52 and E2 would be 1.25. So 1.52 minus 1.25 divided by log of 480 by 120. So if we calculate, so this value would be 0.45 as shown in this plot. Okay. So the compression index we have obtained as 0.45 after plotting the P versus log P data. The void ratio versus pressure data in a semi logarithmic plot. Okay. Now we have got the compression index. Now we'll try to identify the type of soil as normally consolidated or over consolidated. Now how? So that we can determine by calculating the pre-consolidation pressure. Now what is the pre-consolidation pressure? So pre-consolidation pressure you can determine by the Casagrande's method. So by the method which was proposed or prescribed by Casagrande. Now apart from that method, so there are various methods which are available in the literature. You can follow any of those to calculate or to obtain the pre-consolidation pressure. Now apart from all these methods, there is a very handy and very straightforward method. Just you have to extend these two linear segments. So the first linear segment and the second linear segment. So the extension of these two linear segments will basically cut or will intersect at a point. Now the abscissa corresponding to this point will give you the pre-consolidation pressure sigma prime ZC or sigma prime C. Okay. So or sigma prime. So both will bear the same physical significance. So this is the straightforward approach that you have to extend the first linear segment and the second linear segment. Both will intersect at a point, and the abscissa corresponding to this of this point will give you the pre-consolidation pressure. Now, as you can see from this plot, the pre-consolidation pressure of the given soil, what is the value? What is the value of this pre-consolidation pressure? The value is, so this is in logarithmic scale. So we have to rate the scale in this fashion: 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So this means that the pre-consolidation pressure is 60 kPa. Okay, the value is 60 kPa. Now our next job would be to find out the initial effective overburden pressure, that is sigma 0 prime. What is the value of sigma 0 prime? Because depending on that value, means comparing the value of sigma 0 prime and sigma c prime will come to a conclusion about the consolidation type, normally or over consolidated. Okay, so we'll see for the calculation of that sigma 0 prime. Now sigma 0 prime, as you know, it's calculated at the mid depth of this fine grained soil. Okay, suppose here. So sigma 0 prime, for the calculation of sigma 0 prime, you should know, or you must know the individual unit weight of sand and fine grained soil. So sand, the unit weight bulk and saturated are directly given, but for fine grained soil it's not given. So we have to calculate first. Now what is the submerged unit weight? Because the fine grained soil is under submerged condition, so therefore we'll directly calculate the submerged unit weight. Submerged unit weight for fine grained soil, it will be GS minus 1 divided by 1 plus E comma W. Okay, so GS value is your 2.7 minus 1 divided by 1 plus 1.67 multiplied by 10. So that means 1.7 divided by 2.67, so 6.37 kilonewton per meter cube. So this is the submerged unit weight for the fine grained soil. Therefore, sigma 0 prime, it would be 18 multiplied by 2 for the top 2 meter, initial 2 meter portion. Then for the remaining 1 meter of sand, it will be submerged unit weight of sand. So at the same time, you have to calculate the submerged unit weight of the sand as well. So it will be 19.4 minus 10. So gamma sat minus gamma w, therefore 9.4 kilonewton per. Okay, so 9.4 multiplied by 1 plus 6.37 multiplied by 1.5. So this depth is your 1.5 meter. So therefore 18 multiplied by 2 plus 9.4 plus 6.37 into 1.5. So it's approximately 55 kilopascal. Now as you can see that sigma 0 prime is 55 kPa and sigma c prime is your 60 kPa. That means the soil had experienced a maximum stress as compared to its present value in its past geological history. So as per the definition, the soil seems to be over consolidated. Okay. Now we'll calculate the OCR. OCR value means over consolidation ratio. So it's a ratio of past maximum stress divided by the present stress. Okay, so this is your over consolidation ratio. So from this ratio also you can conclude that the soil is normally consolidated or over consolidated. So 60 divided by 55, which is 1.09. Okay, so 1 means it's a normally consolidated, but as you can see it's very close to 1. Okay, 1.09 means it's very close to 1. So that's why at least for this problem we'll assume this soil as normally consolidated. Okay, so though in the actual case it's over consolidated, but the ratio, the over consolidated ratio is very close to 1. That's why we'll be assuming this soil as normally consolidated. So it will basically simplify our job. Okay, so however we are basically assuming, or this assumption is based on the value of OCR. If the OCR value is very higher, suppose 1.5, 2, 3, then we cannot say that the soil is over consolidated, normally consolidated. We have to go for, or we have to proceed with considering the soil as a over consolidated. But for this time being, since the OCR value is close to, very close to 1, we can take it, or we can assume it as normally consolidated soil. Okay, now what is the advantage of considering it normally consolidated? So it will basically simplify our job for the calculation of primary consolidation settlement. Okay, that we will see in the next slide. Okay, now the sigma 0 prime we have calculated as 55 kPa, and since the OCR value is very close to 1, we are assuming the soil as normally consolidated. Okay, so therefore we can utilize this expression for the calculation of primary consolidation settlement. And as you can see, all the parameters involved in this equation are known except this delta sigma value. So delta sigma value, the calculation of delta sigma prime will be our next target. Okay, so this is the clay layer. This is 3 meter thick. This is the fine grained soil. Now what is mentioned in the problem statement? That your due to the tank, oil tank, the foundation of oil tank, when it is in the full condition, it will impose vertical stresses of 90 kPa and 75 kPa at the top and bottom. So this is your, if we draw the vertical stress distribution, if we draw the vertical stress distribution, so it will be something like this. This is your 90 and this is your 75, and we need to calculate, we need to know the vertical stress distribution, your delta sigma prime, at the middle, at the mid depth of the fine grained soil. So therefore your delta sigma prime would be 90 plus 75 2, and this is possible only for the linear variation. So it's mentioned in the problem. that the variation, you may assume the vertical stress variation as linearly distributed in the layer. So that's why we can take an average of these two value at the top and bottom to calculate the delta sigma prime value at the middle of the layer. So it will be 82.5. Okay, so this is the average increase in stress at the mid of the layer. So this is 82.5. So this value is 80. Now we can easily calculate the primary contribution supplement. So SC, your SC, this will be CC divided by 1 plus A0 H log of sigma 0 prime plus delta sigma prime divided by, so CC is your 0.45. Okay, E0 value is your 1.67, H is your 3 meter, and sigma 0 prime is 55, delta sigma prime is 82.5, sigma 0 prime is 8. So 0.45 so it's 0.201 meter. Okay, or 201 meter. So this is the answer to the first part of this problem. That what will be the primary constitution supplement of the fine grained soil layer when the tank is full? So the answer is 201 millimeter. Okay, now we'll proceed for the second part, that is calculate and plot the supplement time curve. So for that we have to first calculate the coefficient of consolidation of the soil, as we can realize from the previous problems. Okay, so for time rate of consolidation, this is the crucial parameter, coefficient of consolidation. Now how we can calculate this coefficient of consolidation? So we can calculate this coefficient of consolidation by two methods, as we have learned from this subject. So there are also other methods, but at least for this subject we have learned two methods by which we can calculate the coefficient of consolidation. Now what are these two methods? So the first one is the Casagrande's method, the method proposed by Casagrande, also known as logarithmic time method, and the second one is Taylor's method, also known as square root of time method. Okay, now for this problem we will consider the second one, that is the square root of time method. Okay, why is it so? Why the name is like this? So that is very obvious from the method. So this is basically CV. So now we are trying to compute the CV value for the given soil using the time supplement data for a load increment from 60 kPa to 120 kPa. So what we'll do first, we'll first plot this time supplement data in this fashion, that time in the root time, so in the x-axis we'll basically plot the square root of time. Okay, and in the y-axis we'll plot the supplement. So these are the data. So these are the data basically plotted based on the given data. Okay, now from the initial portion, we'll basically, suppose this is your A, this point is your A. So from the initial portion, we'll basically draw a straight line AB. So this is the first straight line from the initial portion, it's drawn. Now again we'll draw a second straight line, that is AC. Now suppose this is your O. So we'll basically draw the second straight line to OC in a AC in a fashion that OC becomes 1.15 times OB. Okay, so this is the prescription. This is prescribed by Taylor. Now, what will happen? The second straight line AC, this will cut the time settlement curve at a point. So this will intersect. Now, abscissa of this point will give you the T90, square root of T90. Okay, since the here x along x-axis, it's plotted in square root of time, not in time. So therefore, from this value, your T90 means time required for 90% degree of consolidation. So it will be 1.21. So this is the required time. Now we know this TV for a consolidation of 90%. How? From this equation, 1.781 minus 0.933 log of 100 minus 90. So here U is your 90%. So TV is your 1.781 minus 0.933 into log of 10. So that means 0.848. So if TV is your 0.848, so again we can utilize this equation, TV equals to CV TH dr square. Now from this equation we can calculate the CV value as TV H dr square divided by T. Now TV we know 0.848 or the degree of consolidation as 90%, and the required time we know it's 1.21 minute. Now what's about the drainage path length, HDR? So HDR, first we have to check it's a double drainage condition or it's a single drainage. So for the consolidometer test, it's a double drainage condition. So HDR will be H by 3. So HDR would be H by 2. Now what value of H we should consider, because this H is basically continuously decreasing. So it will be a better, or it would be the best practice if we consider an average value of the initial thickness and the final thickness. Initial in the sense we are now utilizing the data of this stress increment 60 to 120. So we'll consider these two delta H value to compute the initial and final thickness. So it would be the best practice. Okay, so H0 plus HF by 2. Now for this load increment, H0 would be 20 minus 0.21 plus 20 minus it's 1.13. Okay, so 1.13 divided by, so 20 plus 20 minus 0.21 minus 1.13 by 2. So that is okay, this is H, then it has to be divided by again 2. That means by 2. So which is 9.67. I hope that, just let me check it once. 9.67. Okay, so something like that. So if this is the case, then we can easily calculate the value of CV as TV. So TV is your 0.848, T is your 1.21 divided by 9.67. Oh, sorry, I did a mistake here. Okay, so 0.848 into 9.67 square divided by 1. So it's 65.53 millimeter square per. Okay, now if we calculate it meter square per day, so it will be 65.53 into 10 to the power minus 6. Then we have to multiply it with 60. This is in hour, then 24. So it's 0.094 meter square per day. Okay, so yeah, so this is the CV value for the given soil. Now what we will do, will basically we have to plot the time supplement curve, the supplement type curve. So we'll first establish the relationship. So this is what we have done so far. This is for the lab condition. Okay, now we'll concerned about the field condition. Now for the field condition, as you can see, what is the drainage path length? The drainage path length, so it's again HDA by 2. Why? Because it's a double drainage condition in the field as well. So the drainage will occur from both the sides, top and bottom. It's a fractured rock. Okay, it's not an impervious rock. So therefore, your HDA is your 3 by 2, that is 1.5 meter, and CV will not change. So it's 0.094 meter square per day. Okay, so now we can easily establish a relationship between TV and T. So how? TV, it will be 0.094 into T divided by 1.5 square. Okay, so therefore your T would be 1.5 square divided by 0.094. So it's I hope 23 point or around 24 dB. So this is the relationship between time and time factor, as usual we have basically done. Okay, now what we'll do, we'll basically make a table. So the first column, your it will be your degree of consolidation. Then we'll calculate the corresponding settlement. Then we'll calculate the TV, and then we'll calculate the time, which is 24 times TV. Okay, and this will be, yeah, sorry, this will be in days. Okay, so for example, we'll start from 10%, then 20%, then 30%. So in this fashion, we proceed up to 90, 100%, and we will correspondingly calculate the ST value. Okay. So for example, for 30%, so what will be the ST value? So it will be, as we know that U is basically ST by SF multiplied by 100. So your ST will be 0.3 into 201. So 0.3 into 201. So it's 60.3 mm. Okay, because the expected final settlement we have calculated as 201 mm. Now what is the TV value corresponding to this 30%? So it's 5 by 4 into 0.3 square. So 5 into 0.3 square by 4. So it's 0.071. Okay. So therefore your T will be 24 multiplied by 0.071. So that is 1.7. So this is an example for 30%. So you can also calculate for any other degree of consolidation. Now after the calculation, what you have to do, you have to basically make this kind of plot. This is your time, this is your settlement. Now you will basically observe that, so it will basically take a form like this. So as the time is basically increasing, you will be having more and more settlement. Okay. Give me a few minutes again. Okay, so this will be your time settlement plot. So from this plot, you can say the required time for any degree of consolidation. Okay, so yeah, so I'll not uh, go further details about this calculation procedure. So it's a homework for you. So please complete this table and plot the time settlement data. Okay, so in this fashion, then that will complete the whole problem. Okay, so since we are already exceeding time, so we'll end this session by taking another homework problem. And for your kind information, it's taken from GATE 2021. So the void ratio of a clay sample M decreased from 0.575 to 0.510 when the applied pressure is increased from 120 kPa to 180 kPa. For the same increment in pressure, the void ratio of another clay soil sample N decreased from 0.6 to 0.550. Now, if the ratio of hydraulic conductivity of sample M to sample N is 0.125, the ratio of coefficient of consolidation of sample M to sample N is. Okay, so it's a very simple problem. Just you have to know this relationship that CV is K upon MB gamma W. Now, this K is basically coefficient of permeability or hydraulic conductivity. This MB is volume compressibility, and this gamma W is unit weight of water. Okay, okay. Now unit weight of water will not change, so CVM by CVN, it will be simply Km by Kn divided by MBM by MBN. Now this ratio is given as 0.125. Now the only job is to find out this ratio. Now how you can find out? So you can find out in this fashion that MB is delta E by delta sigma prime 1 plus E0. Okay, so you know delta E for both of the cell samples. You know the delta sigma prime, it's same, it's the same increment in pressure. You know E0 value for both the soil samples. So for sample N it's 0.6 and for sample M it's 0.575. Okay, so once you calculate the MBM value and MBN, then you have to basically take a ratio and you have to substitute that ratio in this expression. Then you can easily calculate the ratio of coefficient of consolidation of sample M to sample N. So for this problem also, I am not solving it in its full length. So I am leaving it up to you. So you please uh, solve this problem at your home and let me know if you face any difficulties in the upcoming session. Okay, so this is all for today's session. So thank you for joining this session and have a nice day. So again, we'll meet on next Sunday, that is on 24th March at 5 p.m. Okay, so with this, I am uh, ending this discussion. Okay.